Harmonic excitation of 1 degree of freedom systems. In this section, we're going to be covering how to identify a 1 degree of freedom forced system, specifically simple harmonic forcing, and we're going to be able to find closed-form solutions for undamped and damped systems that are 1 degree of freedom forced with this simple harmonic motion. We're going to be adding a new type of damping to what we're looking at, modeling Coulomb friction in systems undergoing the simple harmonic motion by forcing or displacement. And we're going to begin accounting for distributed masses when modeling our 1 degree of freedom systems. So first we want to look at what is now different now that we have forced vibrations compared to what we saw in the previous section where we had unforced or autonomous or free systems. Now, once we start our timer at time equals 0, we are going to have forcing externally acting on our system. We are going to be supplying or eliminating energy from our system through this external forcing. And it's going to be prescribed in some manner. It could be prescribed in a force that's acting on one of our degrees of freedom directly, or it could be a known displacement of one of our degrees of freedom, which ultimately must be coming from some external force. What this is going to result in is we are going to be seeing a non-zero term on the right-hand side of our equation of motion now. When we are supplying a harmonic input, so just a simple sine or a simple cosine, whether that is through displacement or forcing, we are going to see that at steady state, our system is going to respond with that same frequency but a different amplitude. And we saw this before in system dynamics when we were looking at transfer functions and their related Bode diagrams. We were looking at the steady state response of our systems due to this simple harmonic forcing. However, we were only looking at what happened at the steady state. And now we're going to be able to look at what happens during earlier phases as well. We're going to see that when we are dealing with a 1 degree of freedom system, if we are forcing it at or very close to its natural frequency, we are going to typically produce resonance, where the output of our system, at least the amplitude of it, is going to be very large. Again, we saw this before in system dynamics when looking at the Bode diagram for 1 degree of freedom systems. Near the natural frequency, we saw a spike in amplitude and we saw an inflection point typically in our phase diagram. We're going to see the same phenomenon here, but taking it completely from a time-based observation rather than going into the Laplace frequency domain. And when we're modeling these systems, it's going to be easier mathematically that wherever our forcing is acting, whatever degree of freedom it's acting at, that we want to create our equation of motion and solve our equation of motion at that degree of freedom. So again, we might find it convenient to add additional degrees of freedom to create our kinetic energy, our Rayleigh dissipation, our potential energy, but solving in terms of that degree of freedom where the force acts or where the displacement is located is typically going to be easier. Now, once we've solved for the degree of freedom at that point, then we can relate it back to the other degrees of freedom we might be interested in because we're going to have that geometric relationship or that coordinate transformation already done. So where does this section lie in the grand scheme of what we're looking at in this unit? So again, this unit, we're all about 1 degree of freedom systems and specifically linear systems, which is really the whole course is going to be about linear systems for the most part. In the previous section, we went down this left branch talking about autonomous systems, and relative to what we're going to be expanding to in this section, it was pretty simple. These are all giving us homogeneous ordinary differential equations from the equation of motion. But now going through this right branch, generally talking about forced systems in 1 degree of freedom in this section and the next section, things are going to get more complicated because that right-hand side is now no longer 0 in our equation of motion. So we're going to be looking at all sorts of different types of forcing that could be acting on our system. Periodic or forcing that keeps repeating itself in cycles. We're going to be starting by looking at harmonic systems. And again, we're going to have 2 types of systems we can look at. More simply, undamped systems, which we'll start with, and then get into damped systems where we have energy dissipation. That can be in the form of a viscous damper, which is what we saw in the previous section when talking about damped systems. But now we're also going to consider what if we have Coulomb friction, which is going to be a nonlinear damping or a nonlinear energy dissipation. We could have actually seen this in autonomous systems as well, but we'll look at it here. But some of the same ideas can be applied to autonomous systems. There's no reason we can't have Coulomb friction in those. Then we're going to get into later in the next section talking about aperiodic forcing and more general forcing and how we can solve those systems. We're going to find a general equation of motion for these types of systems. Again, a little bit more complicated because our right-hand side is no longer 0. So we're extending what we saw in that last section. We now have our left-hand side having our dependent variable, here just using x, and then now our right-hand side has some forcing function f of t. When we're writing our equation of motion, we generally want to put our dependent variables and its derivatives on the left-hand side, and any pure constants or functions of time explicitly on the right-hand side. We're going to see that the type of solution we're going to have to this ODE is more complicated because we have to find the total solution to it. So our x of t for these non-homogeneous equations of motion, these non-homogeneous ordinary differential equations, now has two parts. We're going to have the homogeneous solution, which is actually exactly what we saw in the previous section. It's the solution to the homogeneous problem where the right-hand side is 0. And then we have to add to it the particular solution, which is going to be dependent on what our right-hand side looks like. What type of forcing do we have in our system? So again, homogeneous part we actually have already covered. The new thing we have to consider is the particular solution. The homogeneous solution is going to die out over time when we have a damped system. So given enough time, that whole x of h is going to go towards 0, and we'll be left with eventually just the particular solution, which is also going to be the steady state solution. Again, thinking back to what we saw in system dynamics, thinking about that Bode diagram, we were only looking at that steady state solution when we were referring to the Bode diagram. So by the time that steady state solution is the total solution, the homogeneous has died out, or it's gone sufficiently small that our system is just acting in this steady state behavior. A small difference we also saw from the previous section with free vibration is that this total solution, this x of t, is going to depend on our initial conditions. So we can't apply our initial conditions simply on the homogeneous part. We must apply the initial conditions on the homogeneous part plus the particular part. Now, for free vibrations, the homogeneous part was the total solution because in that case where our right-hand side was 0, the particular solution itself was always 0. So in the previous section, x of t was xh, the homogeneous solution. Now again, we must keep in mind we're going to have our homogeneous solution and our particular solution making up the total solution, and that's what we apply the initial conditions on. Now our solution procedure is really going to be exactly the same order that we saw before. When we were talking about free vibrations, we still need to model our system, possibly using Lagrange equations. Maybe it's already pretty simple. We have to identify our equation of motion. Now that's going to get more complicated in this identify step because we have to look at, is it damped or undamped, and what do we have on the right-hand side? For this section, we're only looking at simple harmonic forcing, but we're going to be seeing more complicated types of forcing on the right-hand side that's going to make our solution to the equation of motion look different for each of those different scenarios. We're going to be having more parameters that we might need to calculate in order to find everything we need for the total solution. We need to still identify our initial conditions and then apply them in our fully assembled solution. But for the most part, the techniques we're going to use, the order of the solution procedure is not going to be much different. It's just the specific steps inside this procedure are just going to be a little bit more involved now that we're going to have forcing acting in our system.